Hey everyone, Miss B here, and today we are looking at Illustrative Math, Algebra 1. This is Unit 4, Lesson 8. So, let's dive in. These graphs show the distance d traveled by two cars, A and B, over time t. We have distance measured in miles and time measured in hours. Which car is traveling slower, and explain how you know. So, for this question, we're actually going to look at our rate of change of these. We can talk about how far they've traveled within a certain number of hours, or we can talk about, in general, just the slope of these lines. So let's use some numbers to actually explain, and we will use, let's use 2 hours as our cutoff. So at 2 hours, I have car A looks like it's traveling 75 miles. That's halfway between 50 and 100. So at A, this looks like 2 hours, 75. If we look at car B, again at 2 hours, this has traveled 100 miles. So we're going to say that A has traveled slower because it has covered less miles in the same amount of time. So car A traveled slower because we'll say it went 75 miles in 2 hours, and car B went 100 miles in the same amount of time. Okay. Now you could use a different point on here, or you could use different numbers, but we're just using the same time frame to compare how far they went. All right, so for question 2, we're given a couple graphs. So here are descriptions of 4 situations in which the volume of water in a tank is a function of time. We're going to match each description to a corresponding graph. So I have graphs 1, 2, 3, and 4, and I have A, B, C, and D here. So let's see. We have first, for A, we have an empty 20-gallon water tank. So we're starting at empty. If I'm starting at empty, I know I have to be starting at 0 and 0. So automatically, I know it can't be graph number 1. It's got to be one of these others. So it's an empty water tank. It's filled at a constant rate for 3 minutes until it is halfway full. And then it is emptied at a constant rate for 3 minutes. So to me, that looks like graph number 3 because I am filling this one at a constant rate for 3 minutes. And then after 3 minutes, I am emptying this tank all the way back down to 0. So this one looks like it is increasing for half and then decreasing for the other half at the same rate. Sounds like that description to me. So for A, I would say that this is graph number 3. So for graph 3, I'm going to write here next to it A because we took care of graph 3. Okay, so now let's look at B. A full 10-gallon water tank is drained for 30 seconds until it is half full, and afterwards it gets refilled. Well, since we're starting full, this has got to be graph 1, but we're still going to check that it works for this whole description. We're starting with water in it. We are then decreasing for 3 minutes until it's halfway full. This looks like halfway to me. And then it is refilled all the way back to full. So yes, this would be for graph 1. So graph 1 is going to be B, and we did graph 1. We did A, and we did B. Okay, so question C. A 2,000-gallon water tank starts out empty. It is filled for 5 hours, slowly at first, and then faster later. This one looks to me like it is graph 2, because it is filled slowly at first, which means we have a very gentle increase over time, and then it is filled faster afterwards. And the more vertical my graph goes, or the closer to vertical it gets, I know the faster it's going to be filling. So graph 2 would match up with C. So C matches here, which is graph 2. And then for number 4, we're still going to make sure that D matches with it, just because we want to make sure that we're correct. So this one says an empty 100-gallon water tank is filled in 50 minutes. Then a dog jumps in and splashes around for 10 minutes, letting 7 gallons of water out. The tank is refilled afterwards. So it does match up. We have where it's being filled up to a certain point, a dog jumps in, splashes some water out, and then we're begin filling again until it is all the way full. So this is going to match up with graph number 4 for us. Is going to be D, and we have now all of our pieces matched to our graphs. Okay, let's turn the page. For question 3, we have, Claire describes her morning at school yesterday. I entered the school on the first floor, then walked up to the 3rd floor and stayed for my class for an hour. Afterwards, I had an hour-long class in the basement, and after that, I went back to the ground level and sat outside to eat my lunch. Sketch a possible graph of her height from the ground floor as a function of time. Okay, so we have this horizontal line here. That's going to represent our ground floor. So she's going to be above it when she's going to be on it when she's at ground level. She's going to be above it when she goes to her class that's on the 3rd floor. And she's going to be below ground level when she's got her basement class. So I don't know about you, but when I get to school, if you're entering on the 1st floor, that's ground level. So if she walks up to the 3rd floor, that's probably going to be a short amount of time, and she's going up to the 3rd floor. So maybe we'll say this is top of the 1st floor, 3rd floor, something like that. We actually don't even need to label. We can just sketch a potential graph. I'd rather not label. So she has an hour-long class. She's got an hour-long class. Afterwards, she has an hour-long class in the basement. So she's going to go back down, but not stop at the ground floor. She's going to go all the way down to the basement, stay in another class for an hour. And then she's going to go back to ground level and then eat her lunch outside. So my graph is going to look something like this. I have flat areas where she is staying at that same height above ground because she needs to be in her class for a flat hour of time. So I do need to represent flat areas. I also need to start with an increase, have a flat area. So we're starting with an increase, having a flat area for being in class. Then we are going down to the basement. So we're making sure we cross over that horizontal line, spending an hour in the basement. I tried to make this piece equal to this one here because I was representing those with an hour. Then she's going back up to the ground floor and spending lunch here. Now it doesn't tell us how long lunch is, so I just kind of put an arrow because we don't know how long it is, so she's sitting outside. Now, your graph doesn't need to look exactly like this, but it does need to have the same features. You can make yours a little more condensed than mine. It doesn't have to go all the way over to the end, but we need to have those same sort of features. Let's look at question 4. In question 4, Tyler filled up his bathtub and oops, nope, that's Claire. Sorry. So question 4, let's try that again. For question 4, Tyler filled up his bathtub, took a bath, and then drained the tub. The function gives the depth of the water in inches t minutes after Tyler began to fill the bathtub. These statements describe how the water level in the tub was changing over time. Use the statements to sketch an approximate graph of the function. Okay, so let's sketch an approximate graph. What I'm going to do first is that if these represent points, I may put some points on my graph and then use those to help me draw it in. So if at b of 0 is equal to 0, this tells me that the level of the bath water at 0 minutes is 0. And it doesn't tell us whether it's inches or centimeters. Oh, it does on the side here on our graph. It does tell us inches. So this tells me the level of the bath at 0 minutes is 0 inches, which means I'm going to start at 0, 0. So I'm going to put myself a dot right there. It then tells us the level of the bath at 1 minute is less than the level of the bath at 7 minutes. Now, it doesn't tell us how much those are, but we know that it's less. We also know he's filling the bathtub, so it might have taken him a little while to fill the tub. So it doesn't give me any specific things, but I know I can maybe make a mark for myself where I know at that point it's going to be increasing. So I do have up until like 7 minutes. I'll put a little mark like right here. It's going to be increasing. I'm making that little mark right down here. If you didn't see where I put it, I put a little mark right down here at 7 minutes, just so that I remember that I need to increase until that time, or at least until that time. Now, it does tell me an actual value in my third piece of information. This says the level of the bath water at 9 minutes is 11 inches. So that's an actual coordinate that I can put on this graph. So I am looking for an input of 9, so real close here to 10. And then that level is 11 inches. So if 10 is here, 11 is going to be just above it. So let's actually put a little dot there for ourselves. Okay. I then also am given a statement where some things are equal, that the bath water at 10 minutes is equal to the bath water at 23 minutes. So this might be when he's actually taking the bath, right? Because he's not adding water to it or taking water out. He's just taking a bath, washing himself, that sort of thing. So we know they're going to be equal. And then we have another piece of information here. So before I get onto that next piece, I am going to put a little marker on I'm going to put another marker down here on my axis, so that I can actually sort of see where I'm supposed to be equal. So I'm remembering that I'm increasing to here, but between 10 and 23, which looks like it might be right around here, it's going to be the same. So I'm going to put I'll use red for these. So I'm going to put a little line at 10 and a little line for myself at 23. I'm estimating where those are at. And I know that those are going to be equal. And then at the very end, I have that B of 20 is greater than B of 40. So that means the bath water level at 20 minutes is higher than it is at 40 minutes. So we know by 40 minutes, he should have started draining his bath, and it would have decreased between those times. So I can start sort of sketching a graph here. I know I'm going to increase up here. Now at 10 minutes, I don't necessarily have to have a flat top for my bath here. I can have it be a little bit more curved, but I just have to make sure that wherever I have my point for 10 minutes, I also have my point at 23 minutes. So I could connect these with a straight line. I could say that it increases and then decreases back down. We could do all sorts of weird, crazy things in between here, but we want to make something sort of realistic. So he's filling up his bathtub, taking a bath, and then draining the tub. So this function gives the depth of the water. We can put a little increase in here as long as we make sure it lands back at that point. And then we know that our level at 20 minutes at this point, so our level at 20 minutes has got to be higher up than our level at 40 minutes. So we just need to make sure that at 40, we actually just have a number that's anywhere below, but it makes sense that maybe his bath isn't taking that entire time. Draining the tub means that he's going to drain it entirely, so I'll just say that he's drained it and that maybe there's no water left at this point and we're back at 0. So I now just have to make sure that each of my pieces lines up. I have these ones being equal. I told myself that between here and 0, it had to increase. And then I knew that between 20 and 40, I had to have 40 be lower. So all of these fit. As long as all of your pieces fit in, they don't have to be super specific, but there is one piece we actually needed. Everyone's graph should be at this point here and at actually this point here. So there's two. It needs to cross at 0, 0 and at 9 and 11. So 0, 0 here at the origin, and then this point here needed to be on everyone's graph as well. Filling in the rest, that's up to you as long as you make it work. Okay, and now we're on to the review problems. So we have two functions defined by these equations. Which function has a greater value when x is 3.9? And how much greater is it? So let's evaluate each of these functions at those points. So f of x is 5.1 plus 0.8x. Well, we want to know the function value at 3.9. And writing this function, I write the 3.9 inside. That helps me remember that when I plug something into x, I am actually putting that in parentheses. So I'm going to use 5.1 plus 0.8 and it put in my parentheses 3.9. Now, it's implied that this is multiplication here, so that's actually what I'm going to do. I'm going to do 0.8 times 3.9, and I'm just doing this on a calculator. So it's perfectly acceptable to use a calculator for this point. And so 5.1 is going to stay the same, but that multiplication comes out to 3.12. Okay, so now we're just going to add these together. F of 3.9 is equal to that 3.12 plus the 5.1. That is going to give us 8.22. Okay, so we now have to answer what is g, or the value of function g at 3.9. We're going to do the same thing. We're going to take that number and plug it in. So we're going to take 1.2 and then in parentheses put our 3.9. So g of 3.9, we're going to do 1.2 times 3.9. I'm going to do that on a calculator. 1.2 times 3.9. That gives me, well, 3.4 stays the same, but the answer to this multiplication here is 4.68. So now we're going to take that answer and we're going to add the 3.4 to it. And that gives me 3.9. That gives me 8.08. So in order to figure out which is greater and by how much, we're going to subtract them. I can tell that F is greater, so I'm going to take 8.22 and subtract. So I'm going to say 8.22 and I'm going to subtract 8.08. And that gives me 0.14. So I can say F is greater by 0.14. And that is the answer to this whole question because they asked two things: which function is greater and by how much? And we still have a couple more problems here, so on to question 6. Function f is defined by the equation f of x equals 3x minus 7. We want to find the value. It says find the value of c so that f of c equals 20 is true. So really this just wants us to find an input value to know that this is true. So if f of c is 20, plugging in c would have 3c minus 7. We're going to say 20. We want that to be the same thing as if we took that number c and plugged it in right here for x. So this is going to be a two-step equation. So if you need to put your dividing line to split your equation up, you absolutely can. But I'm going to say whatever we do to one side, we need to do to the other. And oops, if I want to get c by itself, we have to first add 7 to both sides. So that is going to cancel this 7 here on the right. So now I'm going to have 27, and 3 times c is 3c. But in order to get c by itself, we now have to divide both sides by 3. So when we do that, 27 divided by 3 is 9. So we would have c equals 9. And that is the value of c that we need. You can always double check your work by plugging it back in and saying 3 times 9 minus 7. This would give us 27 minus 7, which is 20. So this was my check. Optional step, but highly recommended, especially because you always want to know your work is correct. Okay, let's take a look now at question 7. Function v gives the volume of water in liters in a water cooler as a function of time t, which is minutes. This graph represents function v. What is the greatest volume of water in the cooler? So if they're asking for volume, that is volume of water. It's giving us that. That's an output value. So we're looking here and finding when is it the greatest. It looks like the highest number it goes up to would be 11 right here in between 10 and 12. So I would say about 11 liters, because that's what it looks like to me, about 11. Find the value or values of t that make v of t equal 4 true. Explain what the value tells us about the volume of water in the cooler. Okay, so we want to find input values that give us a specific output. And in order to do that, we're going to look for the output on the left-hand side, similar to when we just looked for our highest point, but now we're specifically looking here at 4. So when we zoom in here, we're looking here at 4. We're going to take this over all the way, and we're going to look for any part where it actually crosses our graph. So I see 2 places, here and here. From both of those, we can look downward to find what input values gave us that output. So it looks like at 2 minutes and at 6 minutes. So we're going to say t equals 2 and t equals 6. So what do these tell us? These tell us that at 2 minutes and at 6 minutes, there were 4 liters of water. That's what they tell us. So at 2 and at 6 minutes, the volume was 4 liters. 2 and at 6 minutes, the volume of water in the cooler was 4 liters. Okay. Now, we do have a part C to this, so we now have to identify the horizontal intercept of the graph. And what does this tell us about this situation? Horizontal intercept is where our graph touches our horizontal axis. So that's our x-axis, or this one here that I have highlighted. It's time in minutes. And it looks to me like it touches our x-axis right here at 4. So I'm going to give this answer, since it just told me to identify the horizontal intercept. I'm going to give a horizontal intercept as an ordered pair. So we do input and then output. So the input was 4, and the output value of the horizontal intercept is always 0. So 4 comma 0, and we can say this tells us that at 4 minutes there was no water in the cooler. Or you could say the cooler was empty. Either way, we're trying to express that same thing. There's no water in it, the cooler's empty, all the water was gone, that sort of thing. So it doesn't have to be my exact same phrasing, because we're just talking about water in a cooler. And then that is actually it for this assignment. I don't have any other questions. So this has been the 3 pages of Unit 4, Lesson 8, Illustrative Math, Algebra 1.